Imagine knowing exactly how much better a language model will get, just like based on its size, the data it's trained on, and the computing power, all that.
Yeah.
That's the kind of power
Predictive power.
that researchers have found with
Scaling laws.
scaling laws.
Yeah.
And that's what we're diving into today. You share their groundbreaking paper with us.
Oh, yeah.
Scaling laws for neural language models.
Yeah.
And I can't wait to really unpack it.
It's a fascinating paper. It really is. It lays the foundation for understanding how we can build and improve large language models, LLMs, those, the kind that power chatbots and all sorts of AI applications. You see them popping up everywhere these days.
Exactly. It's like a glimpse into the future of AI.
It really is, yeah.
So to get us started, what's the big idea here? What did these researchers actually discover?
Well, they found that the performance of these large language models, LLMs, is heavily influenced by three key factors.
Okay.
The number of parameters in the model. Think of this as like the model's brain power. Okay.
The size of the data set.
Yeah.
That it learns from. And the amount of computing power used to train it.
Okay, so it's kind of like a recipe where you have your ingredients, the model size, the data, and the compute power. And by tweaking those ingredients, you can get different results.
Precisely. And they even gave these ingredients handy labels. You got N for the number of parameters, D for the size of the data set, and C's for compute used. What's really remarkable is that they found these factors are related to performance, not just in some general way, but through specific mathematical relationships called power laws.
Now, before we go any further, I think it's important to explain what a power law is, because it's not something everyone encounters every day.
Yeah, no, you're right. It's worth clarifying that for sure. A power law basically describes a relationship where a small change in one quantity leads to a proportionally much larger change in another. Think about like the Richter scale for earthquakes.
Okay.
A magnitude 7 earthquake is 10 times stronger than a magnitude 6 quake. Not just slightly stronger.
Ah.
Okay, big difference. That's a great example. So when they say the performance of LLMs scales according to power laws, they're saying that even small increases in things like data or compute can lead to significant jumps in how well the model performs.
That's it, exactly. And this is a big deal because it means we can actually start to predict how much better a model will get as we scale up these different factors.
So instead of just throwing more data and computing power at the problem and hoping for the best, we can now be a lot more strategic about it.
Exactly. We can use these scaling laws to make more informed decisions about how to allocate resources when building and training these models. Make sure we're being efficient.
This is already starting to sound incredibly powerful.
It is, yeah.
But can you give us a concrete example of how one of these scaling laws actually works in practice?
Absolutely. Let's take the number of parameters, or N, as an example. The researchers found that doubling the number of parameters in a model typically improves its performance by about 5%.
So bigger is better, but not in a simple one-to-one way. It's more nuanced than that.
It is, yeah. There are diminishing returns as you scale up. Doubling the model size doesn't double its performance, but it still leads to a noticeable improvement.
Okay, that makes sense. It's like anything else.
Yeah.
You eventually hit a point where adding more doesn't give you as much bang for your buck.
Precisely.
Yeah.
But even with these diminishing returns, the fact that we can quantify this relationship through a power law is incredibly valuable. It allows us to start thinking about things like, if I have a limited budget for computing power, what's the most efficient way to allocate those resources to get the best possible performance out of my model?
So rather than just blindly building the biggest model possible, we can now use these scaling laws to be smarter about how we approach the problem.
Exactly. And that brings us to one of the biggest challenges in training large language models, overfitting.
Ah, yes. Overfitting. The nemesis of anyone who works with data. Basically, it's when the model learns the training data too well and doesn't generalize well to new data, like a student who memorizes the textbook, but can't apply the concepts to solve new problems.
A perfect analogy, yeah. And the researchers actually found a formula that helps calculate how much data you need based on the size of the model to prevent overfitting.
So imagine having a tool that tells you exactly how much data you need to avoid this overfitting problem. That's what this formula gives us.
Exactly.
That's amazing.
Yeah.
But what's really fascinating is what they discovered about the relationship between model size and data needs.
Yes, they found that data needs don't increase at the same rate as model size. It's a sublinear relationship.
Okay.
As you scale up your model, you don't need to drown it in a proportionally massive data set. The data requirements grow at a slower rate, making it easier to train those supersized models.
This is counterintuitive. So you're saying bigger models are actually more efficient learners in a way. Tell me more about that.
Yeah, it might seem strange at first, but the research really backs up this idea of larger models being more sample efficient, you know? So think of it this way. A larger model just has more capacity to absorb and generalize from the data. It's given like having a bigger toolbox.
Okay.
With more specialized tools, you can just tackle a wider range of tasks more effectively.
Okay, that analogy helps. So it's not just about brute force. It's about having the right kind of complexity.
Exactly.
Handle all those nuances of language.
Exactly. And this leads to another really interesting finding. Remember how we talked about allocating those compute resources? Well, they found that for a fixed compute budget, the most efficient approach is actually to train a huge EE model and stop before it's fully converged.
Now, this is fascinating. It challenges our intuition that bigger models need longer training. You're saying we can achieve better results by strategically stopping early.
That's precisely what the research suggests. It turns out that larger models can learn the most important patterns from the data relatively quickly. Continuing to train them beyond a certain point just yields diminishing returns, you know?
So it's like finding that sweet spot for training an AI, not too much, not too little data. Kind of reminds me of Goldilocks, but with terabytes instead of porridge.
That's a great way to put it, and this actually ties into another concept. They explored the critical batch size. Essentially, there's this optimal amount of data you feed the model at once during training.
Okay, so even if we have tons of computing power, there's a limit to how much data we should give the model at any given time.
Precisely. Training beyond this critical batch size yields fewer benefits, and the paper even provides a way to figure out the sweet spots.
Yeah, that's incredibly useful for anyone working with these models. But what determines this critical batch size? Is it always the same, or does it depend on something?
It primarily depends on the performance level you're aiming for. As you push for higher and higher performance from the model, that critical batch size tends to increase.
It's like training for a marathon. The further you want to run, the more fuel you need to take in.
Exactly. Now, all of this research into scaling laws, optimal batch sizes, and the efficiency of larger models, it's fascinating, but it also uncovers something really mind-bending. A potential contradiction emerges when we think about extremely large scales.
Ooh, I do love a good paradox.
Yeah.
Tell me more. What kind of contradiction are we talking about?
Well, remember how we talked about needing more data to prevent overfitting as the model grows? Well, at some point, the amount of data you would theoretically need for efficient training might not be enough to prevent overfitting.
So even with all the compute power in the world, we might hit a wall because there simply isn't enough data to train these massive models without running into overfitting issues.
It seems that way, and this raises a really fundamental question. Is there a limit to what AI can learn from language? Is there a point where, even with infinite data, our models hit a wall?
That's a profound question. It's like we're bumping up against the limits of knowledge itself.
It's a possibility the paper raises, and it's here that the comparison between LSTMs and transformers becomes relevant. The paper looked at how these different model architectures perform as you scale them up.
Right, LSTMs, those are kind of like the older, more established language models, right? And transformers are the newer kids on the block, the ones everyone's excited about.
That's a good way to put it. While both LSTMs and transformers improve with scale, they found that transformers are particularly good at using longer text contexts.
So transformers are better at understanding language in a deeper, more nuanced way because they can take into account more information.
Exactly. And that makes them better suited for tasks that require a deeper level of language understanding.
Okay, so we've got these scaling laws that help us build better models, but they also reveal a potential limit to what's possible. It's like we're on this exciting journey of AI development, but we're also starting to glimpse the edges of the map.
And that's what makes this research so compelling. It pushes the boundaries of what we know, but it also expands our understanding of the questions we need to ask.
So where do we go from here?
Yeah.
What does all of this mean for the future of large language models and artificial intelligence as a whole? It feels like we're on the verge of something big with these large language models. But if there's a potential limit to what they can learn from data, where does that leave us?
Well, that's the big question, isn't it? It suggests that just building bigger and bigger models might not be the only answer. We might need to explore new approaches to training, new ways of representing knowledge, or even like entirely new types of models.
So it's not just a race to build the biggest LLM.
Right.
It's about being smarter and more innovative
Yeah.
in how we approach the problem.
Exactly. And remember, even if there's a like theoretical limit, you know, we're probably a long way from reaching it. There's still so much we can do to optimize training, find new sources of data, and develop more efficient algorithms.
It's like we've just started to explore this new continent of AI,
It really is, yeah.
and there are still so many uncharted territories to discover.
But going back to that potential limit for a moment, what are the implications of that? What does it say about the nature of language and knowledge itself?
This is where things get really interesting, philosophically speaking. If there's a ceiling to what AI can learn from language data, does that mean there are forms of knowledge that are just like inaccessible to machines? Are there aspects of human understanding that can't be captured in words and data?
It's like asking like what it means to be human. Are we just incredibly complex language models? Or is there something more, something that goes beyond what can be expressed in data and algorithms?
Those are questions that have fascinated thinkers for centuries. And as we push the boundaries of AI, we're forced to grapple with those questions in new and profound ways. This paper doesn't give us all the answers, but it certainly opens up a Pandora's box of philosophical questions that are worth pondering. It's both exciting and it's a little bit daunting to think about. We're on the cusp of this incredible new era of AI, but we're also being confronted with fundamental questions about our own existence and the limits of knowledge.
Yeah, and that's the beauty of these deep dives, isn't it? It's not just about learning facts and figures. It's about exploring the unknown and challenging our assumptions about the world.
Absolutely. This deep dive into scaling laws has done just that. We've glimpsed the future of large language models, but we've also come face to face with some of the deepest mysteries of language and intelligence.
It's a journey of discovery, and the most exciting part is we're only just getting started. Who knows what breakthroughs and new questions await us on the horizon?
Well, on that note, I think it's time to wrap up this deep dive. We've covered a lot of ground.
We have.
And I hope you, our listener, have plenty to think about as you continue your own explorations of this fascinating field.
Keep asking those big questions, Keep diving deep into the world of knowledge. You never know what you might discover.
Thanks for joining us on the Deep Dive.